All right, what do we get for 1A?
25.
25. How about B?
49.
49.
Good job, Henry.
The next one is 256 if I am correct.
If we were squaring, you would be. It's 4.
Oh, it's the square root. That's
Yeah.
why.
Yeah, I don't know.
What do we say about 2B? No solution. So we can do that with one of these bad boys. You could write out no solution. You could put an empty set if you want. There's a lot of different ways of handling it. 3A?
64.
64.
Oh, next one is 125.
Negative 125.
Last March. We're good friends.
All right, number 4A.
3.
3. Cube roots.
Negative 6.
And negative 6.
How did you do the last? Did we get our quiz back?
Math option 4, I believe, is the cube root.
Yeah, I think so.
Oh.
You showed us the grade. About 70.
Where is that?
We'll go out from there. All right, so it says use your graphing calculator to create a data table for these two particular functions, and we want to round our decimals to the nearest hundredth. Right, so, and then I'll graph them both. So I'm going to do it with the iPad because that's still not working. All right, so we have 81, 16.
We're doing math here. Quiet now.
0, 4, 16. 3, 2, 1.73, 1.41, 1, 0. Says error, error, but I'm not writing error. I'll write no solution. The one thing that, I mean, I don't think it's the end of the world, but for some reason the Regents people do. They don't want you to write it, write calculator speak, calculator language on the Regents exam. They want you to write it in math language. So if the calculator says error domain, error dim mismatch, error anything, don't write that because they're not going to give you the benefit of the doubt that you actually understand the concept. They're going to say, okay, you're just reciting what the calculator said, which means that you don't really know the material, right? So use the math verbiage, say no solution, imaginary solution or something like that. Don't use error non-real answer. You know, that's a quick way to lose some credit. Right, so we want to plot these points, but I would imagine only the reasonable ones because 9,81 is not going to fit on the graph unless we scale it. But 0, 0 is beautiful, so why don't we start with that? 1, 1 works in both cases. We have 2, 4. And negative 2, 4. Everything else, I think, is going to go off the grid. Oh, like I think we could get the 9s in there.
Where's 2, 4? Oh, I was looking at that.
3, 9. All right, so just draw my curve here. Y equals x squared is a parabola. We've studied parabolas plenty throughout this course, so that should not be shocking that one looks like that. But the other one, we have, again, just going with the reasonable coordinates, 0, 0, 1, 1, then 2, comma, 1.41, I don't want to plot that. 3 comma 1.7, no. How about 4, 2? And 9, 3. I think I went too high on the last graph. Because I think that was supposed to go to 9. I think I went to 10. All right, so this looks like that. If you graph it on your calculator, you'll see that that's essentially what it ends up being. But if you really think about it, this looks like part of the parabola, but on its side. All right? And so what happens is, if you have the negative counterpart to that, so we have y equals the positive square root of x, but if I had a negative square root of x, I'd have the other half of it going down the other way. The problem is, if I include that, if I have another part, if I actually took this entire parabola and put it on its side, it wouldn't be a function anymore. So I only want one half of it. So it actually makes sense that this is the way it is. Right? But you can see, based on these no solutions here, that while the parabola exists for all values of x, the radical function, the square root radical function, does not. All right? So we have to account for that. So why are all y values for y equals x squared positive? Oh. What happens whenever you square a number? You always get a positive result. Whenever you square a positive result is positive. Why do all negative x values produce an error for y equals the square root of x? What happens whenever you take the square root of a negative number? Square root of a negative number does not exist in the real number system. All right, so it's kind of pointing us towards the idea of domain. All right, so that's one of the things you want to be thinking about when you're establishing the domain of a function. What makes a function undefined, irrelevant here? What makes a function imaginary, or a negative under a radical? And so if I put in a 0, I'm fine. If I put in a positive number, I'm fine. But the minute I put in a negative number, all bets are off. All right. So what we get here, if you read this blurb, it's talking about inverse relationships. So the idea, just the moral of the story here, because the blurb kind of addresses most of it, but it's telling us that if you were to take a point in one function and swap the x and y values, you would get a point in the other function. So for example, we had a coordinate 2, 4 in this function here, right? 2, 4. That corresponds to the coordinate 4, 2 in the other function. All right? So if you ever need to find an inverse function, all you have to do is switch the x and y values and plot the new points. All right? So if I wanted that bottom half, like let's say for example, I have the coordinate -1, comma 1. Plot, instead of that, 1, comma -1. You'll get a point on the new graph, the inverse graph. All right. So we don't do too much with inverses in this course, but we do kind of get your feet wet with the concept a little bit. The idea being that if you have this basic idea down, you should be all right. More than all right. All right, so on the next page, we're talking transformations. All right. And if you go back to the idea that we've been kind of revisiting throughout the course, you have a standard form. Y equals a times the square root of x minus h plus k. All right, we did it for lines, we did it for parabolas, we did it for absolute value functions. Now we're doing it for radicals. All right, so it comes back over and over again. You'll do it for trig functions, you'll do it for exponential functions, for log functions, for other functions that I, like, if I mention the name of it, it'd be like a waste of time because it's meaningless at this point. But these relationships still hold true. So we're talking, I mean, you just go back to what we were looking for when we were describing the graph of a parabola. We talked about vertex and x-intercepts, y-intercepts, things like that. Stretch, shrink, and shift. Those things come into play here also. All right, so the a value is 1. Right, so no stretch or shrink. It's the same as the parent function. All right, is there a horizontal shift?
No.
No, because there is no h value. Is there a vertical shift?
Yes.
Yes. All right, so what I would do is take my parent function as the coordinates of 0, 0, 1, 1, 4, 2, and 3, 9. Maybe not 3, 9 because it's not going to fit. That's y equals the square root of x. I just snagged that from the previous page. And we're just shifting it up, every point up 1 unit. All right. So this is an upward shift. Of 1 unit. So again, if you know that standard form, like in its most general form, a times x minus h, whether it's to the second power, an absolute, the square root, it doesn't matter, and then plus the k, then you're in pretty good shape because the same structure holds. All right. So the next one, what's going on there? Yep, shift 2 units right. So I don't have to plot the parent function again. I have that already. I'll just work off of that first graph. So every point goes 2 units to the right. Provided, of course, I do it correctly. So this would be y equals the square root of x minus 2. All right, and for number 3? What's the negative telling us to do? Reflect over the x-axis. And what's the 3? Stretch factor of 3. Here I'm gonna draw the parent function again, just because I'll have to scroll back and forth and it'll be kind of annoying. All right, so it's up to you whether you want to do it in stages or if you want to do it all in one shot. But ultimately, I have to flip each point over the x-axis. Well, 0, 0 doesn't get flipped, but and then after that, I have to triple its distance away from the x-axis. All right, that's the stretch factor of 3. All right, so I'm going to do it in stages. So first I'll flip. I'll do it as a little dashed curve there. I'll call that the negative square root of x. And then I'm just going to triple each point's distance away from the x-axis. All right, so, well, 0 is not going anywhere. But 1, so 1 distance below the x-axis goes to 3 unit, or 1 unit below the x-axis goes to 3 units below the x-axis. 2 units goes to 6. All right, so we didn't really need all this other stuff here. I just used it as kind of like resources to help me figure out what my function ultimately looked like. All right, but it's up to you how much you want to include, because really you just need the final graph. And then what people will do is they'll say, forget all this stuff, I'm just going to throw that in my calculator and get some points out of that. That's fine also, but this way is going to help your spatial reasoning so that going forward into geometry next year, you're able to pick up those concepts a little easier. All right, so, you know, kind of mix and match the two ideas together and you'll be fine. All right, so on page 4, and this is the last thing I'll do with you because, you know, I'm doing a lot of you today, but the concept of domain and range are what typically people struggle with. So that's where we should spend a little bit of time. But it comes back to the idea of understanding the transformations. All right, so let's talk about the domain of the parent function first, domain and range. So of f of x, I'll just do it off on the side here, e equals the square root of x. The domain, if you just draw the diagram, you draw the graph, the x values start at 0 and they go to infinity. The range starts on the x-axis and goes to infinity. Okay, so without even looking at a graph, I mean, you could look at the graph, don't get me wrong, but if you know these two facts, then you know all of these also. Because all we're doing is we're shifting our domain and range based off of the information that's given here. Is there any shift in the first one? No, so then we should not have to shift our domain and range. So that's gonna remain the same, 0 to infinity. What about this one? We got a shift. What's the shift? 8 to the left. Okay, so that's going to impact what? The domain or the range?
The domain.
Only the domain. So shift that 8 units to the left. But the range is going to remain the same because we didn't shift that. Let's skip number 6 for a second. In fact, I would I'd take it as a typo that 6 and 7 should be swapped. All right, what's happening in number 7?
Did it? Could try it again.
3 down definitely, 2 to the left. All right, so we're shifting 2 to the left, so the domain gets shifted 2 to the left. All right, because domain again is just the left-right. It's the x values. The range is the up-down, the y values. So the range is getting shifted downward 3 units. right? The tricky ones are 6 and 8 because they have negatives. All right, so now the negative, will that impact the x value or the y values of a function?
Y.
The y values, all right, because the negative tells us to do what?
Flip it.
Flip it over the x-axis, all right? So if I had a point at 2 comma 1, it would go to 2 comma negative 1, all right? We're changing the y values, we're not changing the x values. So here, this is telling us that we're leaving our domain alone. Well, that's not true. I'll get to that in a second. The negative is not impacting the domain, but it is impacting the range. So instead of the domain, the range going from 0 to infinity, where should it be going? Negative infinity to 0. All right, because it's flipped below the axis now. Right, so it's all negative values instead of positive values. Now, in terms of the domain, we have a shift here. What's the shift? 7 to the right. All right, so 7 to infinity. And then number 8 puts everything together. So first off, we can deal with the horizontal shift. Right, that's 4 to the right. We'll get that out of the way first.
Negative infinity.
All right, so we're flipping over the x-axis, but then shifting upward 1 unit. So like you said, it's going to be negative infinity to 1. All right, so flipping over the x-axis without that plus 1 there, that would have given us all negative values. So negative infinity to 0, but because we're also shifting it up 1 unit, that's going to bump it up. Instead of ending at 0, it's going to end at a 1. All right, again, all of these can be, you can get them all from your calculator. All right, just look for where the errors are. All right, because if you pop this in, put in 5 square root of x, and look at the x values, you'll see that for every value of x less than 0, you get error, like just infinite error. Starting at 0 going to infinity, you get actual numbers. All right. And the same idea holds for the range. You'll never see a negative number in the range column. The range is a little tougher to pick out in your calculator, but you can always get the domain. Right? The one little trick, it's not really a trick, but one little issue that comes up with the domain in the calculator is if there's a fraction in there, it might not show up in your table. But that's not the end of the world, because most of the time, if there's a fraction in your domain, there's probably a fraction in your function to begin with. You'll look at it and say, oh, I should be on guard for a fraction. I may have to do this algebraically. Right, so, well, anyway, that's that. So I did most of your classwork / homework for you. So, yeah, you just have to do through page 5. But that I think is the hardest part. If you can get a grip on this, you should be good. But this understanding on this comes from the stuff on the previous page. Understanding those transformations. It makes a big difference in understanding how to come up with a domain and range.